In a spectrometer, light from a hot tube of gas is passed through a diffraction grating. The diagram shows the zero order and the first order maxima for the line spectra produced. Explain why different wavelengths are produced by the gas. So this, you need to know a little bit about the structure of the electrons around the atom. So around the atom, electrons are arranged in discrete energy levels. And then remember that if you've got your energy levels around the atom, that the electrons can move up and down these energy levels. So you give an electron energy and it moves up. So you give it energy and it moves up, and then it is unstable and it falls back down, and when it falls back down it releases a photon of light. So electrons can move between these energy levels. They are given energy to go up, get given energy to go up a level, and when they fall back down, they lose energy as a photon of light. So these are the different energy levels: E1, E2, E3, E4 and so on. And these are fixed for specific atoms. They are fixed. The energy levels are fixed for different atoms. So one transition always produces a specific, so one particular transition always produces a specific photon. Fixed frequency photon. So the spectrometer measures the angles between the different lines and the zero order. One of the lines has a wavelength of 650 nanometers and is observed in the first order spectrum at an angle of 19.9 degrees from the zero order. Calculate the number of lines per meter of the diffraction grating. So let's just draw a little diagram of this. We've got the diffraction grating, we've got the light coming in, and then we've got the n equals 0, the 0th order, and then we've got the n equals 1. We've got this is the angle that they're talking about. Okay, and the formula is n lambda is d sine theta, where this d here is the spacing on the grating. So that's what we need to find, the spacing of the grating. So d is n lambda over sine theta. So we've got, it's the first order that we're talking about, so 1 times the wavelength, 650 nanometers, that's 10 to the minus 9, over sine of 19.9. Put that in my calculator. Gives me a spacing of 1.91 times 10 to the minus 6 meters. So that's the gap, that's the spacing, but we want the number of lines per meter. So n lines per meter, n times 1.91 times 10 to the minus 6 must equal 1 metre. So n is equal to 1 over 1.91 times 10 to the minus 6, which is 1 divided by that answer. 520,000. 523,000 lines per metre. Okay, so explain one precaution that could be taken to ensure the accuracy of the measurement of the angle. So there's a couple of things you could do. We've actually got an order on both sides here. So what you could do is measure this total angle and divide it by 2. That would be one way to do that. Measure a bigger angle. Measure a larger angle. This will decrease the percentage uncertainty. Because the angle itself is going to have an uncertainty of half a degree, but the percentage uncertainty, delta angle over angle, if this is much bigger, if the angle is much bigger, then the percentage uncertainty